Welcome to the last class of this course, Geoenvironmental Engineering or Environmental Geotechnology as you would like to call it. We've done 42 lectures in total, including today's lecture. And today we will just review what we have done in this course and what have we learned over the last 42 lectures. So in the beginning, if you recall, we had talked about some learning objectives. Do you recall any of the learning objectives that we had talked about? There were 3 learning objectives to this course. So what we'll do is, we'll go back to the first set of slides, which we saw at the start of this course, and see how much of that we have accomplished and did we actually achieve what we wanted to achieve. So any one of you have your course notes here? What are the 3 objectives?
Concepts and planning of geoenvironmental engineering.
Okay, maybe I will have it in the next slide. So this is what the first slide was when we started the course. We said it's a course on geoenvironmental engineering, also sometimes referred to as environmental geotechnology. It will deal with waste disposal, landfills, slurry ponds, contaminated sites. And there will be 3 lectures per week. And these are the learning objectives which we had sought to achieve. Concepts and principles of geoenvironmental engineering. So it's a new topic, new terminology. What is geoenvironmental engineering? What does it cover? Then the major part of the course would deal with geotechnical aspects of planning and design of waste disposal facilities, which would include landfills, ash ponds and tailing ponds. And we would also look at geotechnical aspects of detection and monitoring of subsurface contamination and control and remediation of contaminated sites. So that's the 3 learning objectives. As we have completed this course, I can add a 4th learning objective. We also wanted to understand how do we rehabilitate the old waste dumps or the garbage dumps that we have. And we also want to learn about the geotechnical reuse of waste materials. How do we reduce the footprint of waste which is accumulating at various places. So when you look at the lectures that we have done, the first 6 lectures were on concepts and principles of geoenvironmental engineering. And after that, we spent a bulk of our time on landfills. So half the course, you see, there are 42 lectures, 20 lectures have been on landfills. So 50% of the course is on landfills, and about 25% of the course is on slurry ponds. Balance on detection and monitoring of contamination and remedial measures, 4 lectures. Rehabilitation of waste dumps and geotechnical reuse of waste, 3. So that's how the course was divided into various segments. So the first 6 lectures, and I will go down the sequence as what we did. We had an introductory lecture. We looked at sources and impact of contamination. We looked at waste soil interaction. We looked at advective flux, diffusive flux. We looked at how much waste is generated and how it is disposed. We also examined the principles of integrated solid waste management with an aim that the solid waste reaching the landfills should be minimized, and we looked at some case studies. So with these 6 lectures, we basically met the learning objective of concepts and principles of geoenvironmental engineering. All these were new concepts and new principles, and there was not much about design here, but definitely what was the scope and what are the guiding philosophies for the various topic. So one thing we became familiar with was this diagram, that everything which is put on the ground causes something to leach into the ground and contaminate the subsoil as well as the groundwater, buried drums, solid waste, ponds, pipelines, underground storage tanks, and that can affect the quality. This is one thing. We also, for the first time, looked at the magnitude of the problems of municipal solid waste dumps, the huge heights they were reaching in mega cities, and the leachate that is accumulating. While municipal solid waste dumps are omnipresent and visible to us nearby, the larger picture was that municipal solid waste is not the predominant waste. We have a lot of mining waste which comes out. We have a lot of agricultural waste which comes out. Apart from that, thermal power plant, industrial waste, and construction and demolition waste. And then we recognize that once you have a waste dump, it's not one or two things it does. It creates a lot of problems, and for different people, different things have different importances. For the person who's driving or flying an aircraft, bird menace becomes very important. For people living adjacent to the dump, odor is a huge issue. The greenhouse gases for climate change, and various other kinds of aspects. And we also recognize that once a plume is formed, the non-reactive constituents travel further ahead. And there are actually 3 zones, one in which the attenuation capacity is completely depleted, one is an active zone, and one has the non-reactive components. And under integrated solid waste management, we looked at the efforts that were underway to decrease the amount of waste reaching the landfills. We talked about various kinds of composting plants, waste to energy plants that would reduce the magnitude of the waste dumps. After the first 6 lectures, we then, of course, got on to the next 20 lectures on landfills and landfill design practices. We started with the principles. We talked about planning of landfills. We spent a large amount of time on liners because they are critical to good performance of landfills. We talked about covers and how they control infiltration. And we had a lecture on the principles of control of leachate. This is more a hydraulic design, and control of gas. So if this was a course on landfill engineering, then of course you would have done many more lectures on both of these. But this is a course on geoenvironmental engineering, which means geotechnical aspects of environmental engineering. So when we did these 10 odd lectures, so in doing all this, we looked at principles of design, the planning aspects, how do you plan a landfill, and of course the design aspects. Just a quick recap, we talked about the fact that cities should have 3 types of landfills, one for construction and demolition waste, which can be reprocessed for gainful use, one for mixed municipal solid waste, and one for hazardous waste. And this municipal solid waste would become smaller and smaller if all the initially collected waste was kept in its segregated form, and you could do composting of the biodegradable components, and you could do energy recovery from the combustible components. And we also then recognized the various types of waste which are coming out in an urban center. And if you have different types of landfills, the municipal solid waste management system has to interact with the hazardous waste management system, because from the industrial area, the non-hazardous waste would come here. And so the biomedical waste, the thermal power plant waste, the sewage treatment plant waste, and other types of waste. So there is a complete interaction between various systems. We also recognized that making a landfill did not mean burying the waste, but it meant that we are preparing a site to receive the waste. We have to bring the land back to its original form It may be a little raised ground, but the same vegetation should come back at the top of the landfill. And over a period of time, this waste should stabilize, and then only it can be considered to be permanently stored. If it is not going to stabilize, say after 100 years, which is the design life of a landfill, 50 to 100 years, then it is only temporarily stored. That means if the waste is still something which can damage the environment, and your liners and covers are not going to survive beyond 50 to 100 years, you have to dig it up and do whatever you can with the waste and replace it with new liners and new covers. Gradually, we developed the concept of a multi-layered system for the covers and for the liners, and we started to look at what a landfill actually looks like in section. And also we looked at how the waste is placed in daily cells with daily covers, and finally a final cover system. And we recognized there are different shapes and sizes of landfills, and we talked about below ground landfills, above ground landfills, and side slope landfills. The composite barrier was a completely new type of liner that we evolved through our discussions. Why is it a composite barrier? How is it advantageous over the other types of barriers we discussed? And how it was there in various types of guidelines and manuals, and how it in fact was not a one layer or a two layer system, but several layers with separators and protectors and filters, and the composite barrier being the key component of the liner system. Similarly, we developed the concept of the cover system, and in the cover system we also talked about various kinds of geosynthetic elements which can replace natural soil, so that you can have steep covers, and we discussed them in detail. Surface water drainage was another area that we briefly touched on. We did not do much detailing of surface water drainage because again it was hydraulic design, but we don't want any water to remain on top of the landfill. We don't want any water to come into the landfill from ground which has a higher elevation than the landfill, and what kind of diversion channels and drains and stormwater basins that we have to provide. We looked at the case study of Gorai waste dump, which has been closed several years ago, and we looked at how its height was increased and how a green cover was established, along with the gas collection facilities and the leachate collection pumps, and including a sheet pile wall, vertical barrier around the base of the landfill. We briefly touched upon how to collect leachate by gravity flow through vertical wells and side slope risers, and by gravity flow in sloped landfills. We also discussed how we collect gas through active systems and passive systems, and through wells and through horizontal collection pipes. So after the first 10 lectures, looking at covers, liners, principles, planning, and looking at leachate and gas, we then looked at some other aspects. One of the main concerns was slope stability of waste dumps, and we also looked at how do you do monitoring around the landfill for detecting whether they will leak. We also did an interesting exercise on costing of the geotechnical components. How much does a cover cost and how much does a liner cost per square meter? And we looked at how landfills are constructed and operated in phases. So again, in this, stability was all analysis and design. Construction and operation covered construction aspects, we had costing aspects, and we had monitoring aspects. So we were bothered about failure within the waste, we were bothered about the failure in the cut that we make to place the waste, we were bothered about failure through the waste of the above ground landfill. We recognized that one of the critical aspects is the failure of the soil or sloping surfaces above the geomembrane, and how this was often found to slip, and we had to take adequate measures. We looked at monitoring, how we are monitoring beneath the landfill, above the landfill, at the boundaries of the landfill, so that we detect early. And one of the philosophical thoughts was, if you are very keen that we should detect leakages early, that we might have to have a double liner system, because that was the only system through which you can actually know that leakage has occurred at a point. Otherwise, even if you put a lot of sensors beneath, you will not be able to detect early, because your leachate could leak from another point. And we brought about the concept of a cluster of wells, so that you are monitoring the well groundwater quality at different depths on the upstream and the downstream direction. And we also became familiar with the concept of multi-port devices. That means in one well, how you can take samples from different depths. We did a very simple method of doing costing of liners and covers, where we were doing per square meter the cost of each of the component, which we could evolve and then come up with values as to how much of 1 square meter of floor area does a cover cost, how much does a liner cost, what is the total cost. And if you were to divide all the costs by the height of the waste converted into mass, then you could tell the cost of waste disposal per ton of the waste. And would any of you remember the cost of disposal per ton of the waste that we had involved, which is an important figure? Pardon? 500, 800, 1000, 1500. There are a large spectrum of costs depending on what the materials cost, the local materials cost, and how the landfill is. How rigorously the landfill has been made. Does it have a double liner system, a single liner system, so on and so forth. Then we looked at the fact that a landfill cannot be constructed in one go, but you have to construct it in phases. For example, here is a landfill which is constructed in 10 years, and how every year you complete and close a phase. There's an active phase and there's an under preparation phase, and how the surface water drainage systems, the leachate collection systems, the gas collection systems have to be developed as the landfill moves forward year by year, and how the final closure of the landfill with measures such as the perimeter fence, the green belts, the major header pipes and drains, we looked at that. Having done slope stability, construction, costing, we moved on and we did some lectures on site selection, settlement, closure and rehabilitation, and we also did some solved examples. And again, in this, site selection is a part of the planning process, and settlement is a part of the design process, and the closure is part of the rehabilitation process. So the important thing is, maybe some of these lectures could have been structured a little early or at different locations, but this is the way the program evolved. And we looked at an example in which, by putting the buffer zones around roads, around water bodies, we could only find, for example, in this figure, these brown spots where landfills could be located, because everything else was excluded by the landfill location criteria. And then we looked at the methodology of CPCB 2003 for selection of sites and ranking of sites, and we looked at how many factors were involved, and then we looked at the weightages and how to arrive at site rankings. We also talked about the settlement of landfills, both the base and at the top, and for the first time we talked about time dependent settlements due to biodegradation of the material, and we talked about this being very significant in comparison to the primary and the secondary primary settlement of the soil beneath it. We looked at old waste dumps all across the country, and we looked at what kind of solutions that one would have to adopt, and from simple covers to municipal covers, to hazardous covers, to gas recovery, to cut-off walls, and to moving and placing in a totally new landfill. All these options we looked at. And we also looked at how to enhance the capacity at a site where the landfill the waste is spread over very low height but very large area, how to relocate the waste, increase the height of the landfill and make a new landfill. And we looked at the example of Deonar. We looked at the example of Deonar landfill in this case. With that, we completed our 20 lectures on landfills, and we came in to the next set of problems associated with waste disposal, and that was for slurry type of waste, which is predominantly for from thermal power stations, coal ash, and from all mining activities which produce tailings. And we talked about slurry disposal on land, the comparison between ponds and mounds, lean concentration slurry disposal, medium concentration slurry disposal, high concentration slurry disposal, the geotechnical properties, whether coal ash and mine tailings are like soil, the planning and design of ponds, how to incrementally raise the embankments, how to do remedial measures in case these embankments fail, and also environmental control measures at these ponds. So we spent 9 lectures on this topic of slurry ponds. And again, we did a lot of planning and design aspects and remediation aspects. So we looked at all these concepts of raising of the dike, multiple raising by upstream and downstream methods, and different configurations on flat ground, on sloping ground, on low-lying areas. We also looked at high concentration slurry disposal technique, which is just coming to India, and also how a ash mound or a dry disposal for such materials is done. Our main focus was on slurry ponds, so we looked at how to plan a pond, what does it look like in plan and section. We concentrated on how the leachate collection systems affect the stability of the dikes, whether they are close, far, whether fine material gets settled on the upstream side or coarse material, and how it affects the upstream raising stability. And we looked at some of the failures which had taken place in incrementally raised embankments and the kind of solutions of remediation which had been arrived at from stability analysis. And how in the end, when the life of a thermal power station or a mining project is over, say after 100 years, you can't just leave a pond and walk away. What kind of stabilization measures you need, densification, covers, self-supported vegetation, green belts, and even liners that are required. And how slurry ponds actually affect the groundwater table, because they are very large in size and the groundwater table rises, and how we have issues about waterlogging on the sides and rising of the groundwater table, and how liners are now becoming increasingly being specified beneath these facilities. In the end, we did a few lectures on contaminated sites. We looked at the methods, we looked at how you detect contamination, we looked at what kind of remedial measures or control measures we adopt for contaminated sites. And that gave us a learning about how we do detection and how we do remedial action. We spent 2 lectures on geotechnical reuse of waste materials, and basically we had a learning about how if we can reuse waste materials which are like soils in geotechnical applications, be the construction of embankments, backfills behind retaining structures, filling of low-lying areas, that would reduce the footprint of the waste. And finally today we are looking at the wrap-up or the closure, and trying to understand what are the new capabilities that have been built in us. What is it that we can do what we could not have done when we started this course. So in contaminated sites, we talked about high-end equipment which can be pushed into the ground with an electrical cone with a filter tip, and how we can also use a special vacuum samplers to take out this and detect what is the contamination at various depths, and how we can then look at remedial measures in terms of control through cut-off walls, and also in terms of bringing back to the original condition by pump and treat, by pumping out and injecting and removing the source. We also looked at reuse of waste, either in the form of compacted ash or tailings in embankments, with chimney drains or with rock muck, or just for road embankments with layers of soil to prevent dust pollution. We also briefly touched on the kind of work which is now going on municipal garbage dumps to mine soil. We are not so sure that the soil is of the quality which it can be used, and whether what is coming out is soil or compost, and that is something which will get sorted out probably in the coming year. But these are the kind of efforts that are going on, and sometimes when you look at this material very closely, it does seem to resemble soil, and therefore there is an opportunity to look at its utilization. But if this has any deleterious material, then we should not adopt it as soil, unless you of course contain it in some kind of a lining system. So that brings us to the final set of slides or slide as to what is it that we have learned which we can do what we could not have done earlier. So any one of you wants to take a call on that I can now do this. For example, you can make a statement that I can join, give me the name of a good environmental consulting organization that you know. I can join ERM Consultants or Golder Consultants as a geo-environmental design engineer. Do you think? So I'm just saying that's one statement which you could not have said in January this year, because you did not know anything about this topic. And believe me, there are a lot of work of contaminated sites in this country, thousands of contaminated sites, thousands of dumps, and there is it's a segment which is generating a lot of work for the environmental consultants. But they can't do it. Their traditional environmental consultants are air and water consultants, and getting into soil and making the difference is where the geotechnical person comes in. So anybody would like to say other than what the example that I have given you? Well, first you have to know which are the top 6 global consulting companies which are in India, and I think you will do well. You will do very well to learn up about them, because you are now at an advantage, and you should know which are the top 6 global geotechnical consultants which are in India, and you should know which are the top 6 national consultants in geotechnical engineering, and you should know which are the top 6 national environmental engineering consultants. This is basic general knowledge. So once you know that, you can see where you can position yourself. But I do know that now built into you is a design capability. And that design capability means that you can be a part of a design team in a consultant's office. So you will learn from a senior consultant or a person who will mentor you, but you would be able to very confidently walk into an organization and say, I can design, I can do this design in landfills. He'll ask you, can you do design of leachate pipe diameter and spacing? You'll say, no, I don't, but I can do it in 5 days, because I can always read up about it. It's not something which I'm blind to. The principles have been explained to me, and I can always go and do the mathematics of the formulae and come back to you. So I think you are in a good position to do this. And you were not in a position to do this before you started the course. Another thing which you are in a good position to do is evaluate. You see, one of the things what happens when you work in the geo-environmental domain or the environmental domain is somebody has to always go and check whether something is harming or not harming the environment. And it's very easy to go, close your eyes, look at the good places where no harm is being done, and say that it is not harming the environment. And this is true for everything. To find the critical locations and to evaluate them and then come up is the important thing. So you don't go hunting for leachate in summer months. Like fundamentally you can't do that. If you do that, there's a problem. But you can go hunting for leachate in the post-monsoon period, and if you don't see even then any leachate outside, you can put a borehole in the center of the landfill, I can assure you, or a waste dump I am talking about, not a landfill. You will find a lot of leachate absorbed by the waste inside it. So you have the ability to evaluate, and time and again, because this is under a regulatory authority, we have a Central Pollution Control Board, we have state pollution control boards, we have Ministry of Environment and Forests, we have state ministries of environment and forests, we have ministries of urban development, we have state ministries of urban development. So we have industrial development corporations, we have state industrial development corporations, everybody is monitoring. So you can also be a part of a performance evaluation team of a regulatory authority. You know more about subsurface sampling than anybody else. You have not done field experiments, but in terms of what type of sampler, how to collect, how to take out a whole sample, that you know more about. So you are, I believe you now have the ability to do this better than most of the other engineers who in the past have not done a course on geoenvironmental engineering. And that is they will do very well air sampling, they will do very well surface water sampling, but to be able to do good groundwater sampling, it's not taking out water from a hand pump nearby. If it is, if the hand pump is polluted, very good, God is kind to you, it is telling you. But if the hand pump is not polluted, it doesn't mean that the 360 degrees around the landfill is, you can always come and give that report. We went to the site, we looked at 3 hand pumps, there was no pollution and everything is fine. But then you should go and say that, no, did you take to sample at 10 meters depth, 20 meters depth, and 3 different depths, 1 upstream, 3 downstream, that ability you have. I also believe you have ability to execute, though you have not gone for any site visit. Have you gone for a site visit to a landfill? How many of you have seen a landfill? Raise your hand. Other than the PhD students. You have? Which landfill have you seen?
I was going back to home and I saw it.
You saw from far and you smelt it and you said, let me run away from here. So you can be a project lead. I mean, I'm not saying you can be just an engineer. Everybody else has to do the work. There have to be waste collectors, there have to be other people who are doing other things, but you can actually be a project lead for executing a landfills project or a slurry pond project. If NTPC wants to build 2 new slurry ponds, they do it in-house, but they also give it out to their consultants. Now, there are some consultants in the energy sector, a few of them I can name, but none of them have that good an expertise in ash pond design. So one can always be a project lead. So see how much of learning has been imbibed in you. My point is very simple. Even if everything you don't remember, at least I hope you will remember the philosophy of what we did, and you can always go and look up a book. You think so? So that's 3 new capabilities. You have 3 more. Isn't it amazing? Even you might be saying, we didn't know we had these capabilities. So one of the things that you can do is bring best practices to the country. To be able to bring best practice, you must have your fundamentals sound clear and crystal clear. If your fundamentals are not clear, you don't know whether one technology is better than the other. Right? One can always read up, but to be able to say that this is a good practice, you need to have strong fundamentals, which I believe this course would have given you. So you should be able to study and refer to the latest codes. I mean, for example, the issue about why has America in 2016 specified liners for ash ponds in the US, and why a full regulatory manual or a code has come out, and what is in it. Now that is something, does it need to come to India? Because we keep on picking up US EPA, United States Environmental Protection Authority manuals for different things. So you have the ability to study and refer to the latest codes without doubt, without feeling uncomfortable. I can't understand terminology. I cannot understand, sir, why upstream method and not downstream method. So you have to study and refer the codes, the guidelines which are bought out by the various countries, the manuals, so that you can incorporate the best global practices in India. I just finished conducting a PhD viva voce examination in Bangalore, and the student had worked on a new system for landfill site selection. But unless that new system is brought down to the field engineers level and put in a manual with the solved example, step by step, it's not going to go anywhere, it's going to remain buried in that PhD thesis. But he has published papers. So one can also, use that side of information. But at the moment what we are saying is that if some best practices have been adopted in some countries, for example, there is this best practice now of adopting geosynthetic clay liners, GCLs. But they can only be used under certain circumstances. In India, what is happening? It is becoming rampant to use them, not caring whether you are putting them on sand or there is a low permeability strata underneath it or not. So they can be used as a part of a double liner system, but people are just using them as a part of a single liner system. So they are good material, and when you don't have impervious soil at a particular location, they can definitely help. But to be able to recognize the best practices, you should be able to read up all the manuals and say, all right, these are the practice, this is the limitation, and this limitation needs to be brought here. Another thing is that a lot of failures are around us. Failures in the sense, slurry pond embankment failures, waste dump failures, contaminated site failures, means the dump is just contaminated the area. To take an analysis of these failures, what has gone wrong, or to do investigation, or to quantify contamination, the extent of contamination, and to arrive at remedial action, even if you are not doing the remedial action yourself, to be able to evaluate proposals of remedial action, you are in a good, strong position to look at them. I again give you an example. I sat in a meeting in which sediments were being taken out from the base of a lake, NMK Lake in Hyderabad. Anybody from Hyderabad? Anyways, so those sediments were polluted. As we said, many of the sediments in water bodies are polluted. And it was being proposed to place the sediments in geotubes as one of the solutions. Now, everybody in the meeting thought that a geotube is like some kind of a treatment system in which the sediment with the leachate will be put, and the leachate which will get treated like your permeable reactive barrier which you were doing yesterday, and what will come out will be good, clean water. I went there, I was called, I think about in the middle of the meetings, 6 had already taken place. I said, look, this is just a blanket. The geotube is just a geotextile. It will dewater the sediment. It won't treat it. Then if you are dewatering it, you have to collect it and then send it to a treatment plant. So my thing is that with the information that you have is in geoenvironmental engineering and your course on geosynthetics, you would be in a much better position to analyze the problems and look at remedial action and adopt one which has very little risk. And finally, in the end, solutions are always being upgraded. Technology is always moving ahead with time, and innovation is the hallmark of improving technology. So what I believe you can do with your background today is to be able to read a lot of research papers and not be scared by the content. Once you are able to read a lot of research papers on the same topic, you are able to put together a comparative table as to what's happening. What was happening in 2000, what was happening in 2005, what was happening in 2010. A lot of people are publishing that I'm doing this, this is the new innovation, this is the new technology. Bring it together and then come out for yourself the state of the art report, what we call a state of the art report, or a critique as to what is emerging. And once you have a finger on it, then you can use that technology for futuristic solutions. You may not be the proposer of the futuristic solution, but you should know it's coming. you should know it's coming. If composting by putting water is going to be overtaken by composting by putting a culture and no water, you better know it's coming, because that's future technology. So this is important. And what I feel is that with your base, you can read up any papers. If you can't understand the paper, you can go back to the book. The research papers are a little more ahead. The books are a little back. See, research papers are the furthest ahead, then the manuals and guidelines, then the books, and the codes are the most behind, because they come out when a lot of experience has been generated. So you can look at, you can do a PhD after looking at all the papers and say, oh yes, this is a gap area. Oh, and if I make this, I can make $1 million company. Go to Stanford, start a PhD, and leave the PhD after you've got your halfway through you've done the work, and just shift out in the innovation and just say, all right, bye-bye Stanford, thank you for the labs, and then start a startup and say, my value, I'm Stanford not passed, and here is my company and this concept. And that is on a lighter note, but you can always go to an innovation hub on the system. So I think these 6 new abilities come to you from this course. Of course, this is an area in which progress is slow in India, because there's not so much money for geo-environmental cleanup. But it is something which is progressing with time, and you will have a lot of opportunities to work in these areas. So with this confidence building end of the course review, and telling you how great you really are, I hope it will make a difference in the long run. Okay, so if there's anything you'd like to discuss about the full course, about the fact that you think no, the 6 capabilities are not there, then we can have a little more discussion. Otherwise, we can stop here. So no thoughts, then all the best, prepare well, and I'll see you in the near future.